Volumes of revolution, the washer method part 2. In the previous video, we took the region bounded above by f of x equals the square root of x, bounded below by the x-axis, and on the region x equals 0 to x equals 4, and we revolved it about the x-axis and found the volume of the solid that it made. In this video, we're going to take that same region and revolve it about different horizontal axes, starting with the line y equals -2. Notice that if we're going to take this region here and revolve it about the axis y equals -2, there's going to be some space in the middle. So I have two notes for you. First note, anytime there's empty space between the region we're going to revolve and the axis of revolution, there will be two radii. The second note, when you draw your radii, they should always be drawn from the axis of revolution. The larger radius should be drawn from the axis to the far side of the region we're going to revolve. I'll call that big R. The little radius should be drawn from the axis to the near side. I'll call that little r. Now these radii really should be on top of each other, but I draw them side by side so we can see them more clearly. So remember that we are revolving really thin rectangles with a width of delta x. And when I revolve this rectangle 360 degrees about an axis, we will form circular disks whose volume is pi r squared times dx. Well, that's just one circular disk, and that's only the big one. So if I were to revolve all of these big radii starting x equals 0 and x equals 2x equals 4, I would get a solid shape with no hole in the middle. So I'll add together the volumes of all of those small circular disks. And then if I were to revolve all of these little radii starting at x equals 0 and going to x equals 4 around my axis of revolution, I would form a different solid shape. And if I add all those small circular disks together, I will get another volume. To find the volume of what we want, we simply subtract the big volume minus the little volume. The only thing missing here are the lengths of the radii. And recall that the length of anything is always big minus small. So if I want to find the length of a big radius, I could do the big y value minus the little y value as such. There are other ways to do it. There are other ways to write it. In fact, I'm going to rewrite this one now, but when I'm finding the length of something, I can always find it by doing the larger value minus a smaller value. For the little radius as well. So to find the length of the little radius, I could do the bigger or larger y value minus the smaller y value. And then simply put these radii into our volume formula. So my big radius is root x plus 2. My little radius is 2. And then we can do the algebra on this to find the actual volume. Note that when I want to find the volume of this first integral, or do the antiderivative, I really need to multiply this out first. So I'm going to rewrite this first part. As x plus 4 root x plus 4. So if I distribute that correctly, that's what we get. And then I'll rewrite this back integral as well. Let me get rid of that square that doesn't belong here. I already squared that. And now we can find the antiderivatives. I will do something first, because I noticed that I have a 4 pi in the first integral, and I'll subtract a 4 pi in the second integral. So those will cancel, so I don't really need to worry about those. I can simply integrate this part with my pi factored out. Antiderivative of root x is x to the 3 halves divided by 3 halves. And then we can plug in our top limit. 4 squared over 2 plus 8/3 times 4 to the 3 halves, which is the square root of 4 cubed. Then subtract our lower limit. And you can simplify that if you would like to. But let's do the same region bounded above by f of x equals the square root of x, bounded below by the x-axis on the interval x equals 0 to x equals 4. And let's revolve this now about a different horizontal line. And I will choose the line y equals 3. My first question to you: how many radii will there be? Well, since there's empty space between my area, the region that I'm going to revolve, and the axis of revolution, I know that there will be 2 radii. I will draw the big radius from the axis to the far side of the region and find its length. I'm going to draw the little radius from the axis to the near side of the region and find its length. Notice that to find its length, I can always do the large value minus a small value. To find the volume that I want, I can sum together all the circular disks formed by the big radius, which gives me a solid shape. Sum together all the smaller circular disks, which form a solid shape, and then subtract the 2. And now we can plug in our radii. Don't forget to square them as such. Let's finish it off. Is there anything we can do to simplify it? It looks like I can, but I don't want to get ahead of myself yet. If we are to FOIL that out or distribute that out, we will end up with 9 minus 6 root x plus x. And I do see that the 9 pi up here and the 9 pi back here will cancel, so I won't integrate those. I will simply integrate this back part. Try not to forget the negative sign right there. So actually, let me rewrite this one. As such. And now we can integrate. I like to factor my constant out when I can. And we integrate x to the 1/2 goes to x to the 3/2 divided by 3/2. I flip and multiply. Minus x squared over 2. From x equals 0 to x equals 4. We will plug in the top limit, so I have 12/3. I certainly could have simplified that. And then 4 to the 3/2. Once again, we get 8. And then minus 4 squared over 2. Plug in the bottom limit, which I really don't need to because it's 0. And then we can simplify. So I get 4 times 8. That is, when I revolve this region about the line y equals 3, we get a shape whose volume is 24 pi.